好，大家做一个 quick sign in，OK？、好，那一样我们today's lecture，大家有没有试着在这个 Moodle 上面试着做测验几次练习？应该都有吧，但是我就看到只有25个人做，OK？那所以还没有做在 Moodle 上面做的，请在 Moodle 上面做一下那个模拟 exam，让你熟悉一下整个线上考试流程。线上考试流程会发生什么问题的话，我已经事先有请提醒大家试着做一做了哈，所以呃如果你有任何问题的话，应该要在这之前提出来，在考试之前提出来，好不好？All right, so let's start today's lecture. OK，没问题。All right. OK，有没有人对于last lecture have any questions？没有的话，today is the last question, last lecture. Okay, next week we will have exam, so make sure you will be on time on the next exam. Don't be late. If you're late more than 15 minutes, I think the exam will not allow you to sign in. So you have to be on time on the exam time. Okay, so please do be on time. All right. If no question, we start with today's lecture. Again, you have any question, please speak up using your microphone. Okay. Okay. All right. Okay. So let's start today's lecture. Today we're going to talk about memory management issue in the operating system. Now, so we're going to first take a look on the background of the memory management. So remember we said in the beginning of the class or beginning of this entire semester, we said that the program must be bring from disk to memory in order for them to run as a process, right? So main memory and register are the only storage that CPU can access directly. Now the register access is in terms of one CPU cycle at a time. Okay, the main memory can take few CPU cycle, CPU clock to access the main memory. Now we have a cache sit between the main memory and the CPU, right? So we have register, well, we should say register, cache, and main memory, okay? So in order to protect the main memory, it is operating system's job to protect the main memory to ensure any correct operation. Okay, so therefore, when you have a process that's running in the CPU, let's say CPU want to access some information, some instruction, you will have to check it's that process is within inside its designated memory space. So for example, you have say a process here, let's say between 3,000 and 4,000, 30,000. Well, let me see, whatever, the 300 to 420940 was in this, right? If a process wants to access this if the memory space, then the CPU will first check its process address, okay, by checking its base and limit register, okay, to check if the access process that access some information is what's inside this memory space by checking its base and limit register. So if it's what's in its base and limit register, it can access the data or access whatever the instruction set is. However, if it tries to access somewhere outside its limit register or before its base register, you will have some kind of error. Okay, so therefore, a program will have what we call some address reference that refers to main memory. Okay, but you have to check if it's what's in the base and limit register. Okay, now, so therefore, a program, okay, or the instruction that bounded between a real process address space or the address space that's logically, okay, So logical address space means somewhere along the line when you write a program, you do not have an actual address space. That's what's inside. That's moving into the main memory. So you use that as a logical space. The real space, the one after you move from disk to a main memory, that's the real address inside the memory space. Okay. So therefore, you have to some way to bound that instruction with the address space. So bounding that instruction and the data to the memory address can happen in 3 different stages. Okay, the first is at the compilation time. If the memory address base is known ahead of time before you even compile, you can generate what we call an absolute code during the compilation. Okay, which means that's a real address space that will not be moving. Okay, after the compilation. So in that case, if the location move, you need to recompile that code. Okay, if that location change, that's at the compilation time. You can generate absolute code. Then, of course, the most of the time is the load time. Okay, it means it generates relocatable code if the memory location is not known at the compilation time. So when you write a program, you try to do a compile, you do not know that program where you're gonna be low at the memory, right? So you just do a compile, so you generate something called logical address space, okay? But when you do a runtime, you can know the exactly location of the program, because when you run a program, you need to load that program into memory and put it into what? From new to ready state, right? Now, so that's at the load time. Another one is at execution time. The bounding of that address space is delayed until the runtime in the process can be moved during the execution from one memory segment to another. That's needed for the hardware support to mapping that, okay, to mapping at the execution time. Okay, we talk about one in each in the later on. Okay, so therefore, if you take a look on this, you have a program, okay, or source program. You do the compilation, such as so the source program could be C, C++, Java, whatever it is. Okay, when you do a compilation or when you do a compile at the compilation time, if you know the location of the program, or if that program's already will be loaded at a specific location, then you can generate what we call absolute code if the location is known at the compilation time. However, if you don't know the compilation time, means when you're gonna when you after you finish compile, usually do what? Run or execute that program, right? When you do a run execute the program, you mean you're gonna load that program into main memory, which you generate what we call the relocatable code, which currently the code's unknown until you load it into main memory. So you delay what? Delay that bounding address after when you finish loading your program into main memory. Okay, so that's at the load time. Or at the execution time means you run at the execution. By the time you run it, you're about to execute, you can use the new address to map to at the runtime. Okay, runtime has a special way to or special function that's we'll talk about a little later, which is you dynamically loading something into the memory. For example, you want to load a specific library into memory for your program. Okay, now, so therefore, by the time you finish, you run, compile, you load that into memory. Once you load into memory, you know the exactly the location of your program by your PCB, right? And PCB has information regarding your base and limit or memory information for your program, for your process. In that case, you can use it, the memory address to refer, okay, your logical address to the physical memory address, okay? All right. So therefore, which brings us to what is exactly a logical or physical address, okay? The concept of a logical address is that which is bounded to a separate to a physical address space, okay? The logical address space or logical address is generated by the CPU, which refers as what we call the virtual address, okay? So you run a specific program, the program that refer to some logical address. They are not at the CPU, they are not at the actual physical address. So that's what we call a logical address. Also, what we call is that a virtual address. Okay, and the physical address is the address that will be seen by memory units, of where that actually your process located a specific location at the main memory. Okay, so in a logical address space or logical versus physical address space, the address bounding scheme for logical and physical address, it's the same at the compilation time, at the load time, but will be different when you actually do the execution. Okay, so it will be different in the execution. Now, to handle that mapping from the virtual address to the physical address or logical address to physical address is MMU. We talked about MMU before, right? Memory management units. Now, in the MMU, okay, the value of that relocated address is added to every address generated by a process at the time when you send it into memory. So when the CPU wants to access some instruction cells, some data in the main memory, at the CPU level, they refer that as what? Virtual address, okay, or logical address. But you need a MMU SID in between to translate that virtual address to actually the physical address at the main memory to get the instruction or get data out. Okay, so at the user's level, the user's program deal with logical address space only. It never see the actual physical address. The actual physical address, they are all being managed by memory management units or MMU. Now, this is what an example of how do you dynamically relocate using relocation register, okay, or what's inside the MMU. For example, you have a CPU want to execute a program or process that refer to some logical address of 346, okay? But that process base register is 14,000, okay? So in that case, MMU simply is adding what 14,000 with 346 and get the actual physical address of 14346 inside exactly the memory address of physical address space was inside the memory. Okay, so therefore, the logical address is mapped into the actual physical address with the base register. Okay, so MMU's function is translate the logical address from the CPU and refer that to physical address or translate that into physical address and get the instructional data out from the main memory and put back into CPU, allow it to do the execution. Okay. So so in that case, this is the most common way to access the data or transfer the data or instruction between CPU and main memory, sitting beside is MMU. Okay. However, there's a concept called dynamic loading. Now, the dynamic loading concept is sometimes the routine is not loaded until it's called. Okay, it's much better for the memory space utilization. Right? Unused routine never get loaded. For example, a library function. Okay, is one type of routine that sometimes you can make it loaded until you call that function. For example, when you write a C program or C++ program, you usually include some library function, for example, including stdio, right? Standard input output, right? stdio, that's in the library function, okay? But you will not bring that function, for example, you call for printf statement, you do not call that printf function until you actually call that function, okay? So when you compile that, you do not actually bring that instruction set into memory until you do the execution. Okay, so this is very useful. Okay, when you have a large amount of code that need to handle infrequent occurring case. Okay, such as error exception. Okay, an error exception only happen once a while. So in that case, it does not need to bring that entire system's error exception handle and error handling instruction set into memory if it does not happen. Only when the exception happen or error happen, then you need to bring that instruction set into memory and let the CPU know how to deal with this error. There's no special purpose for this operating system require or support required to implement. Right? Everything else is implemented through this dynamic loading through a program design. For example, you put a lot of your function into library or instruction set. Okay, so in that case, library only brings in when it's needed. Okay, so that's a good thing. I think your programming 1 and programming 2, 程式设计1、程式设计2, okay, I think been teaching you how to use it in library. So one of a good thing on the library is can run your code very efficiently because it does not need to bring every single instruction set or every single function into the main memory only when you need it. Okay, so that's a good thing about the library. So therefore, in that case, that dynamic loading on that system library only happens at here at the execution time. When you do an execution, for example, you run if else statement or else something happened, then you call that function set into your main memory. Okay, you bring that into main memory. Okay, all right. Any questions so far? 有没有任何问题？好 ，again 有问题，请任何时候都可以问，好不好 ？All right. So therefore, dynamic linking or dynamic loading is linking up responded during the execution time. However, inside your code will have a piece of code called stub, okay, which locate appropriate memory resident library routine, okay. The stub will be replaced yourself with specific address of a routine and execute the routine when it's been called, okay. So then operating system need to check if the routines in the process memory. If it's not, they need to bring operating need to bring that system some routine function into the memory. This is what we call a dynamic linking. Okay. So again, this is very useful in library type function. Okay. System also call that as a shared library. Okay, this is called dynamic linking. Okay. All right. So therefore, a dynamic linking or dynamic loading are quite a good way to optimize your program. Okay, if your program has a huge amount of code that's handling infrequent execution of some instruction set, it's very good. It's a good idea to put it into a library. Okay, so only when that infrequent occurrence that happen, you bring that function or library function instruction into main memory. Otherwise, you don't need to bring it in. Okay, so that's a quick background. So therefore, remember your program all reference most of the time refer as a logical address space. But when you want to actually execute or when you want to access some instruction set of data, that instruction set of data usually in a main memory. Okay, so when you want to execute and you need to bring it from that, you need to link that logical address space to the physical address space in order to access the main memory. Okay. All right, so next thing is a swap. Now, you still remember this, right? So we have a process can do a context switching from one process to another process, means you need to save the PCP, load the PCP to another one, right? So that context switching can happen in specific form, okay? So that means when the program loaded into a ready state in the running because some interrupt or some IO, some events, they need to put it into back to ready or back to waiting, right? Now, if you still remember, the long-term scheduler, or what I call the job scheduler, is the one that select the process to bring into ready queue. So when you do a compilation, okay, when you run and you click run or execute, they need to bring what? They need to bring your process into main memory. Okay, so that means you accept that to put new state into ready state means actually you brought the program from disk to main memory. So that means you bring it from news to ready state. Okay, so at the ready state, every single program, it should be resided in the main memory. Okay, so when you do running is the one you do the execution. Right? You schedule it, you assign to running state. So at the running state, you can also load specific instruction set like dynamic loading. Okay, otherwise, every single instruction set should be in the main memory. Okay, so to run from ready to running is a short-term scheduler, right? To schedule that process into running state. Okay, all right. So when you do an access, all those stuff will be accessed the main memory, right? Now, remember we talked about in the middle, okay? Well, in the from running to waiting, you have another one called midterm scheduling. Now, the midterm scheduling is the one actually swapping out the process from the main memory, okay, and swap back in, okay, to the main memory to continue the execution. This is called swapping, okay? So it means a process might go into execution on the CPU, but somehow, somehow maybe there's a high priority or whatever the situation that caused you to put the CPU, put the process out, swapping out into some memory, into some disk phone type of memory. Like partially swap by a certain requirement, they can swap back into the ready queue. Okay, so midterm scheduling is deal with swap in and swap out. This is what we call swapping. Okay, this is what we're going to talk about today. Okay, now in swapping concept is that when process can swap temporary out the main memory into backend store. Okay, so the process will swapping out from the entire memory, then brought back to the main memory for continuous execution. Okay, so the backend store or the fast disk that's large enough to accommodate a copy of the entire memory image for all users, okay, which can provide direct access to those memory image. Then you can swap in, swap out, or roll in or roll out, which based on some, for example, priority schedule, okay? So the low priority might swap out, so the high priority process go into the main memory for its execution, okay? So therefore, the major time for this swapping is transfer time. Transfer that entire process image from main memory to backend store, okay? Now, there are systems that will maintain a ready queue, okay, to ready to run process, which will be in the main memory, okay? So that's very important. So swapping is swapping some process out of main memory into a backend store, okay? So this is some semantic view, okay? So operating system reside in the lower part of the main memory, right? Then you have a user space, which have many processes that's what's inside the memory space inside, okay? So you might have some process that's in running state, okay? But higher priority process come in and preempt them out. When you preempt them out, you preempt them out somewhere into some waiting state. Means you swap them out and put it into backend store. Okay, you do not put it back into main memory. You swap them out to the backend store. Okay, then later on, if the process, low priority process can able to brought into main memory, then the process image of the process will brought back into main memory. Okay, when you brought back to main memory, that way it will from waiting state go back into ready state. Allow the scheduler to schedule it. Okay. All right. Any question on swapping? Okay. So again, this is still has to deal with the memory management, right? Because the main memory, okay, the space of main memory is finite. Okay, you have only certain amount of main memory. So if so many processes that go inside the main memory, if there's a high priority process comes in, you might swap a low priority process out and put a high priority process back into it. So when the high priority process finish, you can put the low priority process back into the main memory, allow its being scheduled for the execution. Okay, so that's swapping concept, right? Any question on swapping? Okay, if you have any question on swapping, please let me know, okay? All right, so the next thing is what we call a continuous allocation. Now the continuous allocation is this: a process will reside in a continuous of registers address space. So you have a base and limit register. Okay. So the main memory usually are break into two partitions. One is resident operating system, usually held in a low memory space of initial memory space. Okay, when you do load the operating system into main memory. So you still remember how do you load? What's the process to load from from the disk to the operating from disk to the main memory for the operating system when you turn up, right? So that is when you load the operating system into the main memory. So you put it in somewhere in the lower memory area. Then the user's process usually held in a higher memory space. Okay. Then you have a relocation register which use the register which used to protect the process from each other with base and limit register. So you have a base and limit register to protect this process. Base and limit register protect this process. Base and limit register protect this process, right? So we say that MMU is the one sits between to mapping logical address to the physical address state space dynamically. Now, so therefore, in terms of location to access logical address space is you have a CPU try to access logical address space, then you have what MMU to check the base and limit register, and a relocate register which able to access the actually physical address space. Okay, that's the example we've been given, right? So this is handling by MMU. Okay, now, so therefore in the a multiple partition of the allocation means I can run multiple processes at the same time, right? So it means multiple processes will load into main memory. Then in that case, the memory will create what we call a hole, which is a block available of memory, okay, which contains a different size, which is scattered through entire memory. So when the process arrives, if a new process arrives from new to ready state, it needs to allocate memory to find a hole of free space that's large enough to accommodate this process, to fit this process in. Okay, so the operating systems try to maintain the information regard allocated partition and free partition. Okay, so in this example, okay, I have a process file A and 2 initially that's executed inside the main memory, part of memory. So when process A finish, okay, it will leave what? A free memory space, right, or hole in the memory address. Then when the process 9 comes in, it will have what? We'll put process 9 into the one of the free space, and then process 10 comes in, you put another process into the free space, so that the free space now becomes smaller. Okay, that's what we call a hole. Okay, all right. So therefore, it is memory management's job to try to when you load that process into main memory or from a new state to ready state, okay, you need to find a specific free partition and put the process in. Okay, now to put the process in, or how to satisfy that request to I'm going to request a new process comes in to request as a new into what ready state, so that I need to find a free space. So in order to find free space, okay, in the memory space, and there's usually a free approach. Okay, the first approach is very simple. Just find the best fit. Okay, or first fit. Okay, I'll allocate whatever the first free address space or free hole that's available that's big enough to put the process in, and I put that process in. Then I say, from new state, I'm going to say, hey, I have free space enough, and I put it in. You are ready to run, and put you into ready state. Okay. The second one is the best fit. Okay, which allocate the smallest hole that's just big enough for this process to go in. Okay, so in this, the best fit, you need to what? You need to search the entire memory space of memory to find, right, that best fit allocation and put that process in. Okay, in this case, you can produce the smallest leftover, okay, or smallest hole for the process. Okay, the worst fits mean I'm going to allocate the largest hole, okay, which also need to select the entire process. Okay, which produce largest leftover. So I can have a bunch of largest leftover. So I can have another one to put in the future. Okay. All right. So the best fit, the first fit and best fit usually are better than the worst fit in terms of speed, because I do not need to search so much of memory space, and the storage utilization. Okay. So the best fit and the first fit are usually perform better. Okay. Now, however, whether it's best fit or worst fit or first fit usually can create bunch memory fragmentation. Now, the memory fragmentation is I have a bunch of holes that left over all over the memory space. Okay, so there are two types of fragmentation. Okay, the first one is what we call the external fragmentation. Now, the external fragmentation is the total memory space exists to satisfy the request, but they are not continuous. Okay, means in the main memory space, I have memory space that's available, okay, or have free space that's available to put them process in. However, because they are not continuous, okay, means I have 5 megabytes here, 10 megabytes here, 8 megabytes here, they add them all together, you can put a process in, but they are not continuous. This is what we call the external fragmentation. Another one is what we call the internal fragmentation. Internal fragmentation is that the allocated memory might be slightly just larger than the requested memory. Okay, the size difference is what we call the internal. Okay, because it's internal to a partition. Okay, but it's not being used. It's what we call the internal fragmentation. Okay, all right. So if I have a bunch of internal fragmentation, that's the entire thing. The total is what we call external fragmentation. Okay. Now, in order to reduce this external fragmentation, we can use what we call a compaction. Okay. Now, the compaction means I'm going to shuffle the memories, reorder, okay, of place all the free space together into one large block. Okay, means I'm going to start swapping the location of each process, or put all the process continuously one by one. Okay, so in order to create a large block that's available, that can put another process in. Okay, the compaction is possible only if relocation is dynamic. Okay, if the relocation is not dynamic, then you cannot do so. Okay, and it is done at execution time, means before you want to execute, you want to reorder that whole thing. Okay, however, okay, the compaction still have some I/O problem, means if I have a latched job in the main memory, okay, while involving I/O, how should you do it, the compaction, right? Or do I do I/O only into OS buffer? So these are some of the issues, okay, that fragmentation can cause, okay, or reorder that compaction can cause, okay. All right, any problem? 有没有任何问题？ Okay, so this is the last lecture, okay? The exam will request into the last, exam will cover into the last lecture, okay? So you need to know from very first lecture to today's lecture, then we have exam next week, next Monday, okay? Okay, all right. So if no question, we're gonna continue on, okay? 有问题请尽量问, okay? This is your last, well, today is second to last chance to ask the question. Friday will be the last question to ask, okay? All right. All right, so next we're gonna take a look on paging, okay? The first thing we talk about is a continuous memory address space, right? But continuous memory allocation has a problem because we have a bunch of holes left over. Then I need to do a compaction to reorder those processes. But that takes some quite time and it's very complicated to do so. So the next concept, okay, to deal with this, or if to deal with some process that's too large to fit in those fragmentation, another concept is called paging, okay? Now, the paging concept is very simple, okay? The paging concept is the logical address space of the process that can be non-continuous, okay? So the process is allocated physical memory space whenever any non-continuous process is available, okay? So I try to break down the process into pieces of page, okay? So means this. The first thing is you divide the physical memory space or physical address memory into a fixed block of size called frame, okay? So I have a frame for a number of frame for entire memory, okay? So the size usually power of 2 between 512 bytes and to 8,000 some bytes, okay? So they divide the physical memory space into frames, and they divide the logical address or logical memory, okay, into block of the same size called page, okay. So I have a frame in a memory. I have a logical address space or logical memory in as a page, okay. Now, operating system will keep a track all the free frame, okay. And if you want to run a program, okay, the program the size of n frame, right? Then you need to find, n page, and you need to find n free frame to load that program into main memory. So if the program that the size of the program or the size of that process need to have a 5 frame, then I need to find a 5 page. Then I need to find 5 frame to put those page in a main memory. Okay. So therefore, we need to set up what we call a page table to translate the logical address space to the physical address space. Okay, this paging still has a problem. May not have what we call external fragmentation. It still has the problem of internal fragmentation, because you might have if the process have require 4.5 frame, 4.5 page, then you cannot request a half frame. Okay, so it means you 4.5 page need to fit into 5 frame, right? So still left with half page or half frame. That's what we call the internal fragmentation. Okay, all right. 有没有任何问题？好，没有问题的话，we take a look at an example or the address translation for the paging on the memory management. Okay, the address translation scheme is then the base and memory register. Base and memory register is a continuous memory address space, right? So I have a base all the way down to its limit. Okay, but now we break those base and limit or the size of a process into number of page and put that page into frame. Okay, so therefore, the address generated by the CPU now is divided into page number and the page offset. Okay, now the page number is using as an index of the paging table that contain the base of each page in the physical memory, okay, as a frame. Okay, then you have a page offset combining the base register, okay, the base address of that specific page, okay, and define the actual physical address space that's sent into main memory or the memory units, okay. So you can think as a page, 你可以把它想象成是 it's a book, okay, 一本书, right, a book, okay. So that book has a number of page, okay, and page offset is kind of like at the specific page, which line of the text, 哪一行, okay, 哪一页的哪一行, that's a page offset, okay. So then you want to figure out where is the actual physical address space, okay, for that specific instruction, okay. So therefore, you need to find the page number and the page offset in order to get that, okay. So therefore, for given logical address space 2 to the m, okay, which is m will be number of a frame that available on number page, and page size is 2 to the n, okay, a size of per specific page. Okay, so therefore, instead I use base and limit register to figure out the address space or base register to figure out the actual address space. Then the CPU instead access a logical address space. Will add logical address space will give you a page number and a page offset. Okay, so for each of those processes, a page table, right? So that page will be referred to a specific page. From the specific page, and then translate that page. For example, P is page, some page that refers to actually physical page. From the physical page, they replace to the actually, sorry, let me restart it again. For the page, I'm going to translate from page to frame, because frame is the one that actually fit in the memory, physical memory, okay? So I'm translating the page number into the frame number. Then I replace the page number with the frame number along with actually physical address of the offset. This entire thing will be the physical address space. Okay. So you will have a page number and to the physical memory have a frame number. Okay. Let me give you an example. Will be made quite clear. Okay, what the page tries to do. Okay, or paging tries to do. So therefore, for example, if I have a process with a logical address space of page 1, page 2, page 3, okay, to that process, okay, to a specific process, its paging table or page table might look like this, okay. I have a page 0, 1, 2, and 3. This page is a logical memory, okay, to the actually to page table that will reference to the frame number. So the page 0 reference to frame 1, okay, because page 0's information is put into frame number 1. So I have a physical memory space to have a frame number 0, 1, 2, 3, 4, 5, 6, 7. I have a page 1, 2, 3, 4, 1, 2, 3, okay. So therefore, for page 0, referring to my page table, it will refer you to frame number 1. For page 1, okay, it will refer to, based by the page table, I'm going to refer to frame 4, okay. Frame 4 is where I store my page 1, okay. And the page 2, okay, is stored at the frame 3, and page 3 stored at the frame 7, okay. So this is how you get from page to frame, okay. Once you have a page to frame, okay, and the next thing is you want to find out that offset, right? So therefore, we have, say, page size is 2 to the n. The logical address space is 2 to the n, right? So in this case, we have what? N is 2, right? So I have a 2, page size is n to the 2, which is 4 bytes, okay? Then we have what? So we have a page table, okay? Page 1, 2, 3, okay? Which reference to based by the paging table. Page 0 is reference to frame 1. Frame 5, page 1 is referring to frame 6, right? So from there on, if I want to figure out, okay, so this m is 4, so I have a number of frame is what? 2 to the m, okay, logical address is 8. So frame, I have a frame or a page that I can able to store in the frame, okay? So from there on, okay, next thing is, let's say I want to access a specific item, okay? Say item what? Item A, or in the logical, in the actual logical address, right? So first thing I need to translate that 0 page into frame 5, okay? So the frame 5 will give you to frame 5 somewhere around here, right? Frame 5 somewhere around here. The first item is what? The first item, okay, is A. So frame 5 start with the, say, physical address space of 20. Okay, so I have a 0, 4, 5, 8, so on and so forth. At the 20, then I can access this address space, this logical address for item A, okay, at 20. Okay, it is 5 times 4 plus 0 address space, 5, okay, times 4 of the m, then plus 0, okay. So if I want to access, let's say, the item 6 on page 1, So item 6 on page 1. Page 1 will translate into frame 6, sorry. Frame 6. But the item G, okay, is at the location 6, right? Or location 2, you can think of as 2 for at the page 1, okay? So that means the physical address space is what? 6, frame 6 times 4 plus what? The third item, which is 0 base 0, 1, 2, okay, 2, location 2, okay? So which that physical address space is at the 26, okay? So you combine it with the frame and the offset, you get what? Actually physical space, okay, phonological space of page and offset, okay? All right, so that's how you translate the page numbers, paging concept from logical address space to the physical address space. Okay, any question? 有没有任何问题？
喂，
Can ask
老
Chinese
师，
if you want. 请问，
我想问最右边那个 M 2的 M 次方，就是为什么是8？
2的次方就是page， 就是 page， 我有多少个 page？ 应该是说2的是应该说是 offset 我有多少个？2的 n 次方等于4个 byte， 我等于一个 page 里面我有多少个 offset？ 我有4个 byte 的 offset， 所以等于是一个 page 里面我可以做4个 bytes， 你可以这样子想。
那可以再问一下，就是我有点不懂，为什么那个26那个是加2，那个2是什么意思？
那个2就是假设我今天要 access G 这个 item， 对不对？你必须要想哦，这是0 base 的 concept， 所以是0、1、2。
哦，
OK， 所以2是在，所以是0是 start with 这里1、2，所以每一个 page 都是 start with 0 base。OK， OK， 所以你有6乘以，因为我这是4个 m 等于4嘛，所以是6乘以4 ，OK， 然后等于24，因为我有还是有4个 bytes 啊 ，OK， 然后再加上在这个 page 里面的第什么0、1、2第2个 item， 或是 0 base 的话第2个 item，OK，
OK， 好，谢谢老师。
好，没问题。OK， 好，还有没有任何问题 ？If any other question？ OK， 有看到。So relocate the register 去把 page table 找到 process 的 base address 的 friend。对，你可以这样子讲。所以 relocation register 或者是 MMU， 它试着做得到的事情就是，假设我今天一个 program 它给我一个 logical address space， 这个 logical address space 是 page 跟 page offset as a logical address space。那 relocate register 必须第一件事情是先找到 page，OK， 找到 page 之后，这个 page 的 base register 是哪里 ？OK， 再从 base register 加上几个 bytes 去找到 actually physical address。OK， OK， 好，这样有没有回答你的问题 ？OK， 好 ，All right。So therefore, process need to, or the operating system need to keep a track, okay, a list of free frames available, because when the process finish, okay, will go from running state to terminating state. A terminating state going to return every single memory address space that's been used by this process. So therefore, the operating system need to keep a track, okay, where our frames are free, where I can put those frames in, okay. So for example, if a new process comes in, okay, say, hey, my process, the size of my process, I need 4 page, 0 page, 1, 2, 3 page, okay? Then operating system keep track a list of free frames, say 14, 13, 18, 20, 15, I have a list of frames. So in that case, operating system will have to do what? We'll have to allocate the 4 page that's a new process being comes in. So new process comes in at the new state, about to go into run ready state. So before they going from new state to running ready state, they need to put this 4 page into main memory. Okay. Now, so therefore, operating system will need to allocate it. Okay. So if for this full process, I have a 4 page available, have more than 4 page available. So I'm going to put those 4 page into a memory space as a frame. Okay. So in that case, the new process, so the new process constantly requests for 4 frames memory space. When the operating system put those 4 frames into the memory, the process will generate its own paging table. So every single process has its own paging table. Okay. So if I want to access 0 page, now I know based on my paging table, I know 0 page for this process will put it into what? Frame 14. If I want to access page 1, then I'm gonna go through what, frame 13 to find my page 1. Page 2 will be at the frame 18. Page 3 will be at the frame 20. Okay, so this is how you allocate the new process as using a paging concept. So the operating system needs to know, okay, the size of the size of your process, okay, and from the size of your process, how many pages do you need? They need to find a selected free frame and put your process into different frame. Okay, from now on, this process that frame table will be stored into process PCB. Okay, so PCB will know, that process PCB will know where each page located at which frame. Okay, all right. So therefore, to implement a page table, the page table usually keep in the main memory. Okay, the paging table's base register point to the page table. Okay, the page table's limit register are indicating the size of a page, which is the how big the page table will be. Okay, so different process have a different page table size. Okay, then that every single process paging table usually kept in the main memory. Okay, because the PCB always, right? So you only have to swap in and out to the register. Okay, all right. So now in this scheme, every data and instruction on the paging table concept, when you want to access every single data or instruction, you now require 2 memory access nowadays. Okay, one to access the paging table, the other one to actually access the data or the instruction set. Okay, because the first one, for example, if the process wants to go ask for some instruction set, the first thing you need to access what? The paging table, right? Which page table reside in the main memory. So I need to access first time to access the paging table to get from logical address to the physical address. And the second time from the physical address, I need to what? To actually get the instruction or the data. So that require 2 memory access. Okay. Now, the 2 memory access can be solved, okay, if I can have a cache, okay, or first lookup hardware, okay, which is also called associative memory or translation look-aside buffer, okay, or you can think some kind of buffer or memory, cache space, okay. So in some of the buffer I store in some of those address specific identifier. Okay, so in each of buffer entries has a unique identifier for each process to provide address space protection of that process. Okay, now, so therefore you will have a associate memory which you can do a parallel search. Okay, or the cache, right? Do a parallel searching. Okay, so associate memory, you can search a parallel process. You can same thing as you searching the paging table, but that paging table, that part of paging table they are doing in the cache located area. Okay, so if the P is at the associate register, then you get a frame number right out. Otherwise, you need to go get it from the memory table. Okay, so that's how it is. Okay, so before, okay, if you first forget about the middle part of the cache. Before you have the logical address, right? Page and offset. You translate looking on the paging table to find out the friend, to get a friend number, combine it with what? Offset, you get a physical address, right? So before the question is, we have to get what? In order to get this, I need to do first. Remember, the page table is restored in the main memory, so I need to do first what? Memory access, then get a second memory access to get actually data, right? So the caching concept is this. Instead, I have access to this. I put this into some kind of cache. Okay, so I look up a page table. Okay, so I look up the page number. So if it's what's inside this cache, and I can directly get a friend number right out, then I can directly jump to get a friend and get a physical address space. So this thing as a one single memory access. What's that saying? This have to store in some kind of cache. So that's at the beginning we said, if that cache is hit or miss, this is part of that. If that cache hits, means I have that information stored in my cache. I can directly translate from page number to friend number and get the actually physical address. If that's cache miss, okay, then I need to go into actually paging table, which reside inside the main memory, and get the friend number out and get it offset and get the actual physical address space. Okay, so that's the concept. Okay, so caching hits means I can able to get the data right out. Okay, caching miss, then I need to get them out from a paging table. Okay, so therefore you can see the effect on this access time if you want to get a caching hit or caching miss. So assumption is this, okay? If I have some percentage of hit ratio, the percentage of time a page might found in the associative register, okay, means they put into some kind of cache in the CPU or in some kind of fast memory address space. Then in that case, okay, then if I get some kind of ratio, then I can reduce to access, or I can reduce the delay by access the main memory. So for example, if I have 80% of hit ratio, means 80% of time I can find, okay, the required page frame translation of paging table. That's what's inside the register. In that case, I can reduce the access time. So the time to access searching the cache is 20 nanoseconds. However, if the time to access the main memory is 100 milliseconds, okay? So in that case, if you take a look on this, okay, if the caching hit, right, means what? If the caching hits means what? I'm going to search in the cache, which is 20 nanoseconds plus what? 100 nanosecond. I get 120 nanoseconds. Okay. When I do the caching hit, means I access the what cache, then I access the main memory to actually get the data. Okay, that's 120 nanosecond. If it's caching miss, okay, caching miss means I still need to search in cache in order I know it's caching missing. So caching miss. So I search 20 nanoseconds, I find it's not inside my cache. Then I need to access the memory for the paging table, okay, which is another 100 milliseconds, right? Then I'm gonna find out the actual friend number. Then I'm going to access the data, right, in the main memory, which take me another 100 milliseconds, 100 nanoseconds. So the total, if it's caching miss, means I access the cache, access the memory for the paging table, and access the actual data in the main memory, which takes me 220 nanoseconds. Okay, so in this case, if the effective memory access time that was the 80% of caching hit, then I have what? 0.8% of time is 120 nanosecond plus 20% of time is 220 nanoseconds. So effective memory access time is actually equals 140 nanoseconds. Okay, all right. Any questions? 有没有任何问题？ So the calculation here is very easy, right? So you can see the effect. If I have a cache hit, I can reduce quite amount of time for memory access time. Okay, all right. Okay, another issue on the caching is this. I need to do a memory protection because every process maintains its own paging table, right? So you still need to guarantee there's a memory protection, try to prevent any process to access different frame, okay? So therefore, on the memory protection is that they associate protection bits on each frame with valid and invalid bits attached to each entry of that paging table, okay? So the paging table, what's inside that paging table, you will have what? You will have a valid indicating the process associated to that page is a legal page, okay? Able to access that. Invalid indicating that page is not in the process logical address space, okay? So that will be invalid, okay? So therefore, you might have a process with a set of a paging table, right? So I have a page number 0 to 5. So I have 6 pages, okay? To associate to what? To different friend, I will have friend what? Friend page 0 to friend 2, page 1 to friend 3, page 2 to friend 3, so on and so forth. But after the page 5, page 6 will be invalid because page 6 has nothing to do with this process. Okay, so the paging table for this page after page 6 page or page 5 will be invalid item. Okay, to guarantee this process will not access any other people's frame number. Okay. All right. Any questions so far? 有没有任何问题？ Okay, 好，没有问题的话 we continue on. The next thing we're talking about is share page. Okay, a share page is kind of like share code, right? So remember we talking about we have a critical section because we have share segment code, share data file. Those should store into separate part of memory space. Okay, as a share page. Okay, so share code is one copy of read-only or read-write log of specific data or that share code among a process, okay, whether it's a compiler, whether it's a Windows system, whether it's text editor, all the shared part of a code should be stored into shared memory, okay? Shared code must appear in the same location in the logical address space for all the process. So means the logical address space for the shared code should be in the same location or same logical address space for the process. So you have shared memory, then you have a private code and data, okay? Private code and data means each process keeps separate copy of code and data, okay? This page is for private code and private data, which can appear anywhere in the logical address space. So you have shared code and private code, okay? So shared code will be in a same logical address space, okay? So, and also shared code, remember you have to guarantee what? A lock, right? Because the share code is critical section. Okay, remember that. Okay, all right. So this is example of share page concept in a page paging structure for the memory management. So we might have a process 1, process 2, and process 3. So I have process 1, process 2, and process 3. Okay, so you can see the blue one is what we call a share code. Okay. So you will have share code and you will have a data. This is your private code. Okay, this is the private code. So you will have a 3 process. They are all share 3 share code or share page. Okay, which is ED1, ED2, and ED3. Okay, ED1, ED2, ED3. So for if you take a look at for process 1, ED1, ED2, and ED3, they are all same as a logical address space, okay? So you refer to the page table to get the physical frame will have 3, 4, 6 for ED1, ED2, and ED3. So whether it's for process 1, process 2, process 3, they are all have a same logical address, okay? and also they are all referred into a same what? Friend number. Okay, so the friend number or the share code will store at the what? Friend 3, friend 4, and friend 6. Okay, 3, 4, 6. So the data, on the other hand, for process 1, 2, and 3, they are stored in the 3 different what? Frame area. Okay, so this is what the share code will look like, or share page will look like. You have a same logical address space, which you refer into same frame number, which actually refer to a same actual physical address space. Okay, then each of those processes can access those share page. Okay, however, you need to guarantee to have some kind of access because they are all in terms of critical section. You can use the read line, you can have the write line, so on and so forth. Okay, all right. Any question? 有没有任何问题 ？OK， 好，没有问题的话 ，Let's take a look on a structure of the page table。来，还是我们要休息一下？你们要take a break 吗？我有点 jump ahead，我应该中间应该先问你们要不要休息一下下来。Anybody need to take a break？有没有人想要 take a 10-minute break？ Or we continue on？好，那我们休息一下下好，我们休息个13分钟好了。We come back at the 4:50， 4点50分，好不好？中间如果有问题的话，你们可以问。OK， 好吗？OK， 好。So we come back at come back at 4点50分 4:50。Okay. All right, you can do a quick sign off, sign back in the 4:50. Sign off for break.
老师想问一下，
来，请问，
讲义第30页，
好，
刚刚那个好像有同学有问，就是那个 logical address space 那边，然后那个东西是指它 logical memory 的大小是2的 m 次方是吗？
对，
那下面那个8 page 这个数字是怎么来的？
这个是8 page，是 actually 你有多少 page 在 memory 里面？
哦，所以左边那个等号不是直接从上面那个式子来的？
左边这个
就是
等号，
这个8 page， 我说最右边的那个8 page。
右边 ，OK， 右边这个8 page，OK， 这个它是跟你讲说整个 total 你有多少个 frame，就是这个这个可以变，可以 change，because 有 memory 大小是不一定的，但是 frame 应该是说 memory 的大小会假设我有这个 memory 我有512个 MB 的话，那我可能就会 break down 成多少个 frame，OK，那多少个 frame 就可以 fit in 多少个 page，对不对？但是 number of page 是 based on 这个 process， 这个 process 可能会有 number of page， 这个会是不一定。
了解。
OK。
好，谢谢老师。
OK， 没问题。但是frame 跟 page size 是一样，哎，因为我要把 page 放到 frame 里面去，所以你看，如果在这个 example 里面，我这个 page 假设我可以放4个 item， 哎，所以我这里面也要有4个 item， 譬如说就会是0、1、2、3，然后第4就是下一个 frame， 4、5、6、7就是另外一个 frame， 8、9、10、11这就是另外一个 frame， 哎。所以这个 frame size， 这个 frame 的每一个 frame 的大小 跟每一个 page 大小要一模一样，因为你最后要把 page 放到 frame 里面。那 page number 跟 offset 就会给你一个所谓的 actually from logical address space to physical address space， 因为你要把 page 转换成 frame， 然后 offset 还是 offset，OK？、所以 n， 所以我们刚刚看向上一个，我记得有一个 n， 去，我没有讲 size of n 嘛 ？OK， 好，那所以 n 就是 actually 什么 page 大小 ，n minus n 就是 page number，OK？、那对 actually 你要从 page number 转换成 frame，OK？、你就要 take 了刚刚的 paging table，OK？、那 frame number 是 m，OK？、然后 total 你会有多少个 page 或多少个 frame 可以 fit in 多少个 page，OK？、
哦，好，谢谢老
好，
师。
没问题。
所以你那样说的意思有8个 page， 是因为我这块记忆体有32个 bytes， 所以按照那个 page size， 按照那个 size 去切的话就是8个。
对，
所以跟那个 m 等于
7
都没有关系。
没有。
OK。
M 可以定成任何一个，就是你的 memory 的多大，你就可以放到多少个 page 多少个 frame， 你可以 divide 成多少个 frame。
我看它放在一起，我以为那个8是来自上面的。
哦，是。
OK， 谢谢老师。
没问题。好，如果没有问题的话，我们就4点，我刚说4点50嘛，对，跳好快，4点50 we come back，OK？、那 I'll stick around at the online， 如果你有任何问题的话，你可以任何时候发问，好不好？ OK， 好，大家好，那 we come back to the second half of a lecture. OK， 一样 sign in, quick sign in, sign in. All right. OK, while you sign in, we continue on. OK. All right. So last time we talked about paging, right? So the next thing we want to look on the paging table, the structure of the paging table. Okay. Now we say the page table can grow very, very long. Okay. So therefore we might need a way to break down the paging table. Okay, because every time you search in the paging table, it's the time you wasted before you execute an execution of the process. So there are three types of a structure of the paging table. First one is hierarchical paging. The second one is hashing. The third one is what we call the inverted paging table. Okay. The hierarchical paging table is simple. Okay. It basically breaks down the logical address space into multiple of the paging table. Okay. This is a simple technique of a two level, for example, of a paging table. Okay. So you have an outer layer paging table, inner paging table, then you actually refer to the frame. Okay, so this is the outer paging table to tell you, okay, I'm at certain page, then from that certain paging table, then I go into access the frame. You can think of this as a book. Each book has a chapter, right? A chapter and a page, okay, and a page and line number. OK， 所以你可以把它想象成它是每一个章节，每一章，然后每一章，然后第几页的第几行。You can think of this way. OK, so in the example of a two-level paging is this. OK, if you have a logical address space is 32 byte machine with a 1K of paging size, can divide it into, for example, a paging number consists of 32 bytes and a paging offset of 10 bytes. Or you can break down, since the paging table is page, the paging number can further divide into 10 bytes and a 12 byte of offset. Okay, so therefore the logical address space nowadays will look like this. Okay, sorry, the offset, actually I type it wrong again. Okay, it's I think it's a 20 and a 12 bytes of offset, page offset, because doing without the page offset. Okay, sorry about that. Okay, so therefore the paging table might break further divided into 10 and 10. Actually, the 10 and 20 of page offset. Okay, so you might have what it look like is this. You might have page number. Right, of 10 bytes and 12 bytes, then you have a page, sorry. So you might have 10 bytes for the first outer layer, 10 bytes for the second outer layer, then the paging offset. So P1 is indexed into outer layer page, P2 is indexed into displacement page, then you have a page offset. So you can think of as 第几章第几节的第几行. Okay, you can think of that. Okay. All right. So in this case, the beginning we're learning is that we have one level. Okay, one level you have a page number. Okay, with a page offset. Right, that's one layer. Page number, page offset. Then the second layer you might have what? You might have a page number 1, which index into second page. Outer layer page table. Page P2 is displacement what's inside the page for the outer layer page table. Then you have a page offset. Okay. And you can continue on, means that the first outer layer I have what? I look at the specific outer layer page table to find out at which page. And then which page defines on the page, different page, you have a second offset, okay, to find out which page. From there on, I find out the offset of the item. Okay, so that's two layer. Okay, of course, that two layer can be multiple layer, 3 layer. So it means now you have a second outer layer, inner layer, then offset. So you can continue on to break down. I think the most currently right now it's a 7-layer page, and you have a 1, 2, 3, 4, 5, 6, 7 all the way down to offset. Okay, so that could be a 3-level of paging. Okay, so you can have up to 7 layer of paging, or you can have N layer of paging. Okay, means you have each directing to the other one. So the concept is still the same, very similar to paging. Instead you just using paging and offset 每一页到每一行，你可以把它想象成是每一章、每一节、每一行，甚至是每一本书、每一章、每一节、每一行。Okay, think of this that way to break the memory management if the memory gets very big. Now, the second one, okay, instead I order into the specific order of paging, like using a hashing table or hash paging table. Okay, a hashing page table is that if you take a look at that, you have a common address space, square, and 32 bytes. Then you can have a virtual page number as a hash into a specific paging into a paging table. The paging table will contain what's inside the paging table will contain a chain of item of the hash into a send location, like a hashing bucket. Okay, if you have 2 items into it, you can have put it into send location. So you have a virtual page number which compare with this chain and searching for a match. Okay, if match is found, you can have a corresponding physical frame. This will be extracted. For example, okay, you have a logical address space, you have a page number and the offset, right? So instead, I'm looking for the paging table, or I using hashing function to find out where this P is hashing to. Okay, from the hashing table, we direct into a set of what? So the paging number is hashing into some hashing table or hashing bucket into it. You can think of it. From that hashing table, I have to search in a linked list that's linked toward to the other one. So it might be P, Q, P, O, whatever that is. So I'm gonna search the linked list sequentially to find if this item's here, if this item's here. If this item's here, you will get what? This is actually the friend number that's stored in this linked list, right? Then you restore that friend number to here, and you get the actually physical address to find in the physical memory address space. Okay, all right. So that's hashing table. Okay, so you hashing the friend number, and you're looking at a hashing function, find out hashing bucket. What's inside the hashing bucket? You might have a multiple page. Then you just sequentially search that linked list to figure out where is that friend number is. Okay. Now, the third one is inverted paging table. Now, the difference between inverted page table is this. In the paging table, each process has associated paging table, right? So every process has its own paging table. So one entry for each page of that process is using or the virtual address of that. But the problem is if you have a million entry, you will contain a large amount of physical memory for the paging table for that process. Okay. Now, in the inverted paging table is this. Instead, I'll let the process to have its own paging table. The inverted paging table is they have one entry for each real page or frame of the memory. Okay, remember frame number equals page number, right? Okay, a number of frame equals number of page. Okay, so therefore, inverted page table is that I have one single long table, inverted paging table. Okay, that directly refers to exactly the memory size of number of frame. Okay, so each entry of the virtual address of the page will store into the real memory location, which inform about the process, which has information of which process on that page. Okay, this you decrease the memory that needed to store each page table. Okay, before each process is on page table. Now I have one single giant page table for the entire memory. Okay, however, it increased the time it needs to search in that page table when a paging reference occurs. So instead, each process refers some page. It just searching its own paging table, although that page table should be small. But okay, you have memory number entry of each process paging table. in this case, inverted paging table is I have a single paging table, but that paging table is quite big. So this will increase the searching time, okay, to searching the paging table if a page is referred, okay. Now, of course, you can use in the hashing table to limit the searching, okay, or at most few of that paging table entry, okay. Now, the inverted paging table will look like something like this, very similar to the paging table, okay? But instead, I searching PID, okay? That PID would look on the PID and the page offset to find out the actually what? The frame number of that physical address space. This entire paging table is the entire memory frame number of frame, okay? That's inverted paging table, okay? Compared to the paging table concept, each process has its own paging table. Then each process will find out its page number to frame to find out frame number, okay? But to here, this entire paging table is the entire number of frame in the physical memory space, okay? Then the paging table, when you do a searching, you're just searching that what page number along with the PID to make sure this process can access this paging table, this frame, and get the frame number out, okay, and get the actually physical address space, okay. That's the difference between the paging table and inverted paging table. All right, okay, so frame number is page number equals frame number, okay, frame number equals page number here as well, translation, okay. All right, so that's it for today's lecture, okay. Any questions? 有没有任何问题？ Okay. 好，没有问题的话 ，Today is the last lecture. Okay, Friday is a review. Okay, a review of today's lecture. But most of the time, you should start practice on the online exam. Okay, 请大家稍微练习一下，所以请大家去Moodle 看一下 Moodle， 看一下这个 online 的 exam。我现在看，我看看。好，现在大概有31个人已经试过了，然后我们 total 我们这一堂课大概有，我记得有50个人，所以还有蛮多人没有play around with 这个online exam，OK，所以你要是有任何问题在 online exam 操作上面，你也可以问我 ，OK， 你如果今天才试的，你可以礼拜五试着问我看看你有没有说发生什么问题。那有不清楚的地方一样，你可以在礼拜五问我Otherwise, any other question? 有没有任何问题 if any question at all, you can ask me before the exam. Okay, the exam is next Monday. Okay, the exam is next Monday. It's only 1 hour and 50 minutes. Okay. All right. So you will need to have your phone ready. Okay. 如果我上个礼拜讲的你没有听到的话，我们模拟考主要正式考试主要会是这样。我想想看怎么去 click 正式考试。所以考试前一定要有一个密码 ，OK。哎，我可不可以重新开始？这样不行，重新开始。好所以正式的考试的时候，你一定要有考试密码嘛，对不对？然后你要用你的手机登录Google Meet， 然后摄像头打开，然后打开的所以你需要用一个手机稍微撑住你的手机。那主要你要撑住的方式，我要你照的大概的状况是你的脸、你的手 ，OK， 大概是这个样子 ，OK。然后荧幕这边会有那个 Moodle， 会有 Moodle login， 那 Moodle 你没办法 copy and paste 在那个 setting 上面，然后一次只能作答1题，是以顺序式的作答，但是这个排序呢会是 randomly 跳的，所以每个同学会收到的顺序会不一样。OK， 是 open book 的，所以这个 exam 不会那么简单，所以你稍微心里要有点底。你必须要融会贯通整堂课的这个 concept，OK，do not copy，OK， 绝对不要就是 copy and paste，或你也没办法 copy and paste，但你不要抄，就是因为我会把你们的答案统统再跑一次那个抄袭的那个 program。如果上面有太多抄袭的这些东西的话，你会被打成0分，所以绝对不要抄袭，用自己的话来解释题目。所以但是我并不觉得那个题目可以在网络上找任何答案，所以exam will be open book, open notes. Okay, yeah, that's about it. 哎，有没有任何问题 ？exam 或者是今天的课，或是之前的课？好，那如果没有问题的话，那 that's it for today. You guys are free to go. Again, sign off. Okay. Try to practice the online exam again. If you have not done so, okay, then you have any question, you can ask me on Friday. All right. Okay. You can sign out and you're free to go. Okay. All right. Hey, 有人有要问问题吗？我没有听到你讲任何东西啊。
老师，我想问一下 Lecture 08的内容。
好 ，Lecture 08，好，你等我一下，我刚刚找到 Lecture A 的东西。好，哪一页？
讲义的第36页的部分。
36页，好。这一页吗？
老师，你的 Lecture 08跟我的好像不太一样。
那我再往上还是往下 ？Lecture 08嘛，对不对？
是在 synchronization 的。
synchronization。等一下，我去那个网络上的应该是你 download 的吧？对，等我一下，我直接去网络上看。Lecture 08。32，你说嘛，对不对
36。
36，好 ，OK。36。好，这边嘛。
对。
好。
我不太清楚它那个 test and set 的这个函数是怎么运作的。
test and set 其实如果你回来看36的话，好，我们先去看，我看看36，我看一下。test and set 其实很简单 ，test and set 它只是要 check 就是如果这个进来的这个 boolean variable 在这个 address 里面 ，OK 是 true 还是 false，OK， 然后如果是 target 等于 true 的话，我就 return，OK RV，OK。那我们来看一下这个 test and set 的 follow，OK。其实 test and set 的 follow 是这样子，如果我把它打开一点。Test and set 的 follow 其实是这样，你 first take a look，因为 initially 我们 set lock equals to 4嘛，我们才可以进去嘛。然后我们做 test and true， 然后我们把 lock set 成 true，OK。test and set 在这里面的 lock， 因为 lock 一开始 equals to 4，对不对？lock equals to 4的话，我们在这里面会把它的 target 设成 true， 然后 return 它，OK。我设成 boolean， 然后一个出去，然后就是 return 这个东西 ，OK。那表示我一开始设成 for 的话， 我会把 log 换成 true， 把它，因为它给我把它 set 成 true， 然后 return 它嘛，对不对？
哦，
OK， 然后接下来呢 ，enter the critical section， 但是我 exit critical section 我把 log set 成，所以 OK，sorry， 我们在这边好了 ，log 等于 true 的时候我 enter the critical section， 但是我假设我的 t time T4 进来的时候 process 2也要进来，对不对？我的 log 现在是 true， 但是我 test set 如果是 true 的话，我会什么还是 true， 对不对？然后表示我在这里面会 stay in the while loop。在这里面我们刚刚一开始是 for 的时候，我会先什么？我会先出来，但是我会 set 这个 log equal 是 true。
了解。
OK， 然后最后这边就会 stay in the while loop， 一直在做交换的动作，直到这个 process access the critical section set the log 等于 4。当它 set the log 等于 4的时候，这个 test set 的时候，我先 test 然后 set 它 ，test 然后 set 它。我一 test 的时候，我就变成 4了，但是我 set 成什么？我把它 set 成什么 ？true 啊，我把它 set 成 true，然后我就进去set 成 sorry， 我应该要 set 成 true test and log equals to 4， 但是我会把它 log 再 set 成 true， 然后会 enter the critical section， 就像这里一样，我的 log 在这里 enter the critical section， 这也会变成 true， 直到它 exit the critical section。OK，
好，了解了。
好，没问题。
谢谢老师。
好，没问题。好，还有没有任何问题 ？OK， 好，一样哈。我的建议就是多试试看 online exam 啦。只要你主要是比较让你能够熟悉整个 process， 才不会在中间考试中间出状况。那 otherwise， you have to understand， 就是the operating system 我会问的东西都是 open book 的 exam， 所以稍微会难一点点，会花多一点时间在 answer each of those questions。OK， 然后不应该要跟同学讨论是 open book， 但是没办法，不应该讨论talk to HR 的。OK，All right， 好，还没任何问题。
老师是教到哪里考到哪里，是这样子，
就是教到今天就考到今天，对。
那这一章是没有完全上完，对不对？
这章就是看，这章我就是考到 invert the page table， 就这样子。
哦，好，谢谢老师。
没问题。OK， 好 ，Any other questions？ 有没有任何的问题呢？好，again I'll stick around，OK， 到5点20 ，if you hear any question you can ask， 或者想到。如果你真的还有一些问题，你是看完今天的 slide， 然后上完课的时候有一些问题不清楚的，你可以礼拜5再问我，是 quite OK，OK。